Today we're going to go over Riemann sums, which is a way to approximate the area under a curve. Okay, before I teach you how to utilize Riemann sums, I should tell you more about it. Imagine you have a curve such as this. Just an inverse curve. Now, Riemann sums works by drawing rectangles. There's three different types of Riemann sums. There's left Riemann sums, right Riemann sums, and middle Riemann sums. Left Riemann sums work by taking a certain point on the curve, drawing that out over a certain interval, and finding the area underneath. And then it takes another interval, does the same thing. And it's always from the left. And you can tell that this isn't very accurate, and Riemann sums in general is not very accurate. However, both the AP calculus AB and BC test for it. So this works by multiplying the interval. Let's say this is 1, 2, 3, 4, 5 for the x values. And this is this could be 40, and this could be 25, and this could be 20, and so on. And so what this would do is you would multiply 40 by 1 to find this area here. You'd multiply 25 by 1 to find this area, 1 by 20, and so on. And it is, as I said earlier, not a great approximation. Now there's also right Riemann sums. Let's say we have the same curve here. This works by, right Riemann sums is pretty similar, except it takes it from the right at a certain index and finds the area here. Oops. And it does the same thing. And depending on the curve, this could be either an over approximation or an under approximation. Now, of course, as you can see, they aren't very accurate. In this instance, the right Riemann sums is an under approximation. The left is an over approximation. So what can be done to increase the accuracy of this? Well, there's also, as I said earlier, I believe, a middle Riemann sums. So let's say we have the same curve, just an inverse curve, I believe. Rather than taking this point here and extending it, or taking this point here and extending it, we can find the middle index. So let's, I'll elaborate. Let's say this is 0.1, this is 0.2, 3, and 4. And let's say this here is 20, this is 25, this is 40. So you may begin by taking, let's say you're using a left Riemann sum, you would extend this to 1, find the area underneath. If you were doing it right, you would extend this over to y to x equals 0 and find the area underneath. What if you could find the midpoint and just draw a rectangle? It's not perfect, of course, this is still an approximation, but it's halfway between a left and a right Riemann sum, and as such is much more accurate. Now this works by multiplying the height. So it works by finding the x midpoint and plugging that into your equation, whatever it is. And from there, you can find the y value at this midpoint and multiply it by the entire index, if that makes sense. So let me just draw a mini version over here. Let's say that this curve is y equals 1 over x. And we're told to approximate the area underneath the curve with 3 rectangles using a Riemann sum. Well, if we're going to try to make this as accurate as possible, we would choose this index here, 0.5, this here, 1.5, and this here, which is 2.5. And we would, I should probably redraw this. What we would do is find the y value at this midpoint. So we plug that in, we'd see that y equals 2. So now we have let's say this point here is 2. This point here is 2. We're going to multiply it over the entire index, and that's what the area of one rectangle. And we're going to repeat that. We're going to plug this in for 1.5. We're going to plug 1.5 in for x, I should say. Plot it. You don't necessarily have to plot it. This is better. I prefer visualizing the Riemann sums, but put that on your curve if you wish, and just extend it, multiply it by 1 in this case. And that's our second one, and we would do that again right here. And as I said earlier, this is not perfect, but it is decent. Okay, this is practice problem 1. We're told that there's a curve y prime equals 2x plus 1. Using four rectangles in the left Riemann sums, approximate for or approximate y between this interval. So we could draw this out. It's best not to, because some curves are very difficult to draw out on the tests, the AP test, and it's not worth your time. It's best to just visualize any curve, essentially, or at least the process for finding a Riemann sum. So we're going to say that y between that interval is equal to what we're going to want to find. We're using Riemann sums. We're using 4 approximations, so we should first find the y values when x equals 0, when x equals 1, 2, and 3. And I suppose I could draw this out. This is not going to look anything like the curve. That's not necessary. Just imagine the general process for finding a Riemann sum. So first, we're going to find the y value at 0, the x value at 0, the y value at x equals 0, and we're going to extend that till y equals 1. The y value at x equals 1, and extend that here. The y value at x equals 2, extend that here. And the y value at x equals 3, and extend that. And by multiplying this y value and this x value, we can find that. The area underneath that portion of the, not underneath, we'll be able to find this rectangle. We can do that for here as well, here, and here. So the y value at y equals 0, I suppose I should probably just, sorry, not y equals 0, y prime equals 0, because I named this curve that for some reason. So we're going to want to find the y prime value at x equals 0, and we're going to multiply that by 1. Because you can tell that these indexes are equidistant apart. It's not always the case, but in this, plus the y prime value of 1 times 1 again, because that's the distance between these two indexes, plus y prime of 2 times 1, plus y prime of 3 times 1. You can tell that by doing this, by using this setup, we have 4 rectangles. So y prime of 0 is 1, plus 3, plus 5, plus 7. Okay, so y from the y from the y on the interval 0 to 4 is equal to 16 approximately, using a left Riemann sums and 4 rectangles. Okay, this is part of a problem from the 2015 Calculus BC FRQ. Keep in mind that Riemann sums is a Calculus AB topic, and so this may be a little more complex. And so it's fine if you don't understand this. Let's focus on this part of the question, because this deals with Riemann sums. We have the speed of Johanna, and we're asked to find the definite integral from 0 to 40 of the absolute value of v of t dt. What does this mean? Can we approximate it with a Riemann sum? This is the only part we're actually interested in. This, if you must know, is the total distance covered by Johanna. from t equals 0 to t equals 40. But that doesn't matter. We're just trying to find what it's actually equal to. So we'll say that the integral from 0 to 40 of the absolute value of v dt is approximately equal to, and now we have to come up with this actual problem, a right Riemann sums. So we're going to find and the 4 subintervals indicated in the table, which are 0, 12, 20, 24, and 40. So naturally, with a left Riemann sums, you would use that interval, that interval, that interval, and that interval, and you'd end up with 4 subintervals or rectangles. But with a right Riemann sums, remember that you have a graph sort of like this. Well, the graph may look nothing like this, but this is the process of a right Riemann sums. You take it from here, you bring it over here, and you multiply. So what we're doing here is we're using this interval here, this interval here, this interval here, and this interval here. Okay, now we have to actually solve the Riemann sums. So the y value at this point is equal to 200 times 12 plus 240 times 8. And the reason it's 8 is because that's the distance between this interval. So I guess I'll draw this out one more time. Imagine this point here is 12 and this is 20. And this is 200 and this is this right here is 240. And you're trying to find the triangle from here to here with a right Riemann sums. You're going to want to find the y value of 20, which, okay, should be 240. Let me redraw this actually. So you're going to want to find here, and you're going to want to bring it out to 12. So we're multiplying by 240, but we're multiplying 240 times 8. So that's why we're doing that, I suppose. Okay, so let's write this out further. Actually, let's simplify this. Or not simplify it, let's just write the general Riemann sums. We're going to want to find v of 12 times 12. Absolute value, by the way, because that's what it asks for. Plus v of 20, absolute value of v of 20, times 8. Plus absolute value of v of 24 times 4 plus absolute value of v of 40 times 16. Okay, and from here, we can plug these in. 200 times 12 plus 240 times 8 plus the absolute value of v of 24, which in this case is 220, not negative 220. And that, of course, is multiplied by 4 plus 150 times 16. And that is equal to 7,600. Okay, this video was a bit rushed, I admit, so some things may seem rough around the edges. If you like this video, subscribe, and in the comments, if you have any suggestions for future videos, put them down there.